educational buildings involving unique design processes throughout Colorado. She is a founding member and president of the National Organization of Minority Architects Colorado chapter, NOMA Colorado, and is a lecturer for the College of Architecture and Planning in their undergraduate and graduate level programs. Thank you, Patricia, for joining us today. We will now begin with today's division. I want to thank all of our fantastic sponsors that make this all possible. And our first presentation today will be Ferris State University. Ferris State, if you don't mind coming on camera and bringing your slides up, please.
Are you guys able to hear me?
We can hear you. Thank you.
Awesome. Well, good afternoon, everyone. We are Beyond Desk Design from Ferris State University, and today we will be presenting Heartwood, the first elementary school in the Grand Rapids area, catering for children with disabilities. My name is Cassandra Dudlow, and I am the team lead. With me today, I have Lexi Bainbridge, Jesus, Lexi Brummel, Brandon, Corey, and Destiny. Our industry partner is Michigan Solar Solutions, and our design partner is Tower Pinkster out of Grand Rapids, Michigan. Heartwood is a year-round elementary school catered to the needs of students who have ADHD, autism, Down syndrome, dyslexia, are hearing impaired or visually impaired. Located in Granville, Michigan, we believe that elementary school is crucial for core academic abilities and socialization skills. The school's name was derived from the center of a tree, also known as Heartwood, which is a support system for the entire tree. The footprint of the building is circular with areas branching off so that navigating the building is easier for our students.
We have three main design goals. One is nurture through nature, where we strive to merge nature to Heartwood's vast arming wings. Build with empathy, we understand that every student has their own individual needs and are especially tailoring each wing to meet their accommodations. And finally, we are integrating sustainable systems to improve environmental quality as well as increasing learning opportunities to the community.
Here's our site plan, which shows where our school is located on the property. We put the building on the southwest part of the site due to that area being higher in elevation and easily accessible from the street. Additionally, since the building is higher up, views of the surrounding trees and pond are an added bonus. You can also see that we have a path leading from the school to the park and pond where there is a lookout dock so that students can observe and be engaged with the environment. Our target market for this project are parents and guardians who want to give their children the best and most specialized elementary education, but also give them a year-round school option, which isn't available in the nearby areas. Lastly, we want the students to focus most on their creative curiosity and life skills at a more relaxed rate. Here's some data that we collected based on the location of our elementary school. This will help us choose the building materials and make design decisions.
Heartwood is a 2A construction using a shallow foundation, classified as a Group E building occupancy. The sprinkler code and parking ordinances were all followed, and all codes were found in the 2015 Michigan Building Code based on the IBC from 2015. As Cassie stated earlier, the design concept is based around a tree. So as you can see from our center courtyard, we have sections branching off, and in those sections, they're going to be better suited for the needs of the students in that area, such as the visually impaired on the right side. You can see the floor plan is a little bit more open, and it's just safer for them to get through. And then here in our center courtyard for our rendering, all wings will be having access to this courtyard for them to be able to gather around and learn in. And then for material selections, we decided to go with a lot of bricks, concrete. We wanted to use woods that are native to this area. And we also wanted to use some biophilic walls because we know that's important for kids at this stage.
This project will utilize HVAC systems like a geothermal heat pump and forced air and ventilation. The R values exceed the Michigan standard, and the air changes per hour to accommodate for students sensitive to diseases. Solar and wind energy will be placed on and around the building to achieve our goal of net zero.
Moving on to our market analysis, we took a look at Kent County's population as a whole. We found out that in the population, 12% has a disability. One of the big advantages to our school is that we have a smaller student to teacher ratio, which has a lot more one-on-one time for students and teachers to interact. Roughly, there's about 10 to 15 students who will be enrolled in each grade level, and overall about around 300 to 400 students enrolled at one time. We cater to Kent County and surrounding counties. Being a student in construction management, I was able to help this team create an estimate of approximately $19 million.
One of the ways that Heartwood shows durability and resilience is through its use of power. There are solar panels being utilized as the building's main source of power. This system also has a backup generator tied in to ensure that the school is able to run continuously when others couldn't. Towards the back of the site, there is a pond that will serve as the site's natural water runoff. To assist this process, there will be small bioretention areas made up of native plants to help prevent erosion on the site. This will also create a learning opportunity for the occupants.
To us, it's important that we use locally grown and manufactured materials for Heartwood's construction. So we took the time to do some research and pick out the best local companies for the materials and the construction process.
Some of the integrated performance that Heartwood demonstrates is the use of solar panels that obtain 2.5 to 3.5 hours of peak sunlight a day. The solar panels combined with a geothermal heat pump save 30 to 70% in heating and 20 to 50% in cooling per month.
As we mentioned before, we have 6 wings that will be placed around Heartwood to optimize each student's learning. Some examples that we achieve this is quiet materials that will create quiet environments for the students with autism and Down syndrome, while increasing acoustical properties for the hearing impaired. For the comfort and environmental quality, we will be using a daylight harvesting system that will turn off lights in relation to the natural light entering the space. Wireless sensors can control indoor temperature, humidity, and airflow. And natural light will be optimized year-round.
Our preliminary EUI is 42.62 without solar and wind energy. With the integration of these systems, we are on target to have a net zero design. We will continue to reanalyze this data throughout our final design decisions. This is our estimated project timeline. After completing our semifinal presentation, we plan on finalizing our design decisions and analysis on energy impact. We will also fine-tune our integrated systems and cost analysis. Finally, we will refine our deliverables to satisfy the solar decathlon requirements before presenting our final design in Golden, Colorado. On behalf of Beyond Desk Design, I would like to thank the judges and all those listening in for spending time with us today. We are excited to continue the development of Heartwood and are now prepared to answer any questions you all may have.
Thank you so much. That was an excellent presentation. Patricia or Catherine, do either of you have any questions? Please feel free to come off mute.
I have a question. As far as citing the building and also coming up with the form, could you go back to where you talk about that and why some areas seem to be extending further than others? I think it's an interesting Yes. Could you speak a little more about like how the cafeteria, the gymnasium, the cultural enrichment and communal classes, for example, are kind of stepping or fanning out the way that they do?
Yeah, I can answer that one. Can everyone hear me?
Yes.
Perfect. So a lot of it has to do with just different viewpoints on the site. We wanted to be able to make sure that other areas in the building also had an equal opportunity to have the views that we do have on the site, such as the pond. There is a golf course across from us as well, so the landscaping is really nice on that end. So just giving them more opportunities to have glazing and natural light, so it's not all just one flush wall.
Okay. And when you were, trying to provide more opportunities for light, how about the directional location of all of these spaces? Right. For example, students with autism is maybe facing northeast if the plan is north. Could you speak on that as well?
So are you just talking about why we had placed it there on the northeast side?
All of them, like the entrance faces south, those kind of things. What decisions did you make about the directional the direction of these spaces, which direction they face?
Yeah, so for the entrance, we wanted to put it closer to the already existing street, so then the parents can have the drop-off center straight from the street, so they can drop off their students. Also, like Jesus mentioned, we do have visually impaired students closer to the entrance, so they don't have to navigate the building as much. Whereas the students with autism and ADHD are more on the quiet end of the school because they do need less distractions. Also going off of that, the hearing impaired students are the furthest away from the parking lot because a lot of the times they won't be able to hear any oncoming traffic. So it's just safer for them.
Mm-hmm. Catherine, do you have questions?
I do. I have several.
Okay.
So could you go to the slide with your market analysis and your dollar amounts and funding? And how did you arrive at your $306 per square foot? Have you looked to see what? So I'm assuming this is a private school since we've selected this specific population. Is that assumption correct? Private school? Okay. So have you looked to see on the construction cost of this private school in relationship to what is funded by the public schools is going to be very different. This one, of course, is costing more per square foot in that Michigan area. And then I'm also concerned with the cost to attend this school. So I don't really guess I have a question. That's more of a comment to be sure that as you progress that you double check that market analysis. Also as a private school on our durability and resilience kind of criterias, a lot of times our communities use our schools whenever we have a climate or weather event. Is it your intention for this school to be used by the community or even just the stakeholders, the students who go to this school, to be a location where they can come in a climate event, especially since it's a special population? So I would leave that one is a question. I mean, have you considered how it could be used by your population?
Yes, so it is a year-round school, so it would be open, especially in the case of any weather emergencies as well. We do have a basement, though it is not accessible to the public regularly, just because it is going to be where maintenance rooms are and the HVAC systems. We could also utilize the basement in case someone needs to take shelter for perhaps a tornado and other events like that.
And to add on to that, the school is also utilizing solar panels along with a backup generator to make sure that the school has power even in the worst case scenario. So for Michigan, we get a lot of snowstorms and ice storms, and we would absolutely make sure that the school has power for people to rely on.
And then actually location of your engineered system specifically. Really glad you brought up the
Catherine.
generator. Oh, I'm sorry.
Thank you. We're up with
We're at
time,
time.
unfortunately,
Thank you.
and trying to keep it fair to all teams. So thank you very much to Ferris State University. We really appreciate the presentation, and thank you, Catherine and Patricia, for your questions. We are going to move ahead with Wentworth Institute of Technology now.
All right, can everybody hear us all right?
Ken.
You can take a few minutes to get your slides ready to go and prepare yourself.
Everybody good?
Yep, and we can see your slides. And Catherine and Patricia, are you ready for them to start? Thumbs up will work from you two.
I'm just trying to pull up the scoring.
That works. This is the first time switching between projects, so we'll give you an extra
Exactly.
couple seconds here.
Thank you. Good to go.
All right, so good afternoon, ladies and gentlemen of the jury. We are Wentworth's educational design team from Boston, Massachusetts. Today, we will be introducing to you the Nubian Square Elementary School. The school aims to bring 21st century learning into the heart of Roxbury, Massachusetts. The design supports a play-based learning curriculum, encouraging children's natural imagination creativity through the use of winding ramps as a circulation. When we began this project a month ago, the team and I, including Jack, Rex, Ivan, Oscar, Brendan, and myself, we were thinking a lot about which type of site in the area could really benefit from adding a new educational program. Roxbury, Massachusetts stuck out to us immediately demographically as an area that would benefit. The area is very culturally diverse. Major of its residents are middle to working class adults with a very large population of school-age children. The site itself currently stands empty, so everything we'll be doing to it is proposed. The public social spaces in the area include the playground. There are central to supplement educational spaces like the library seen above, and there are very convenient methods of public transportation to and around the site using the local bus and T stations. Looking at the site specifically, the significant factors we've been analyzing as the sun path, prevailing winds help us determine the building's orientation, while the site grade seen in the section to the right here reference the upper right, oh my God, results in flood risks that I'll utilize later in the building systems. In terms of site access, like I previously mentioned, the entry to the site is from a primary road that connects to the bus drop-off and the building entry that exit onto a tertiary road that helps alleviate traffic during the time school gets in and out.
There are some passive strategies that we're using on the site scales. So as we mentioned, the floodwater risk, we actually have a bioswale as well as a gray water storage that collect this as seen in the section reference at the top left. And we are also utilizing stack effect in our high volume spaces such as atrium, library, and the gymnasium. And then continuing, we are also daylighting is important to the learning experience and is placed in areas where daylighting will be most effective throughout the day. For additional control, we propose operable shading, and its results are in the top left, without and then with operable shading. Sun exposure, wind, and noise are all factors that have influenced our facade design. Our facade detail proposes a two-layered facade, an internal paneling system that has bubble windows to control light and aperture while creating a playful experience for the children, while the external shading are panelized louvers that allow a significant variation in depth.
Examining our key atrium space becomes simple through the section perspective. Here, our systems that we utilize are clearly exhibited. So for our atrium space and the rest of our building, we use a geothermal heat pump supplemented by an ERV system to both cool and heat the space throughout the year. Within the atrium, we have, and then auxiliary to that, we have a water collection system that will help with providing water for our bathrooms and other auxiliary spaces.
Our building program is divided into two forms, learn and nourish. Learning spaces contain resources for the children's mental growth, while nourishment spaces contain resources for the children's physical growth, such as the gym and cafeteria. The program division also allows public spaces like the gym that also in auditorium, which is also also the cafeteria, can be public access spaces without outside of school hours, and it separates it from the more private classroom and learning spaces. So here's a conceptual diagram of our atrium design, where the ramps are utilizing a more playful circulation throughout the space, and interior courtyards and gathering spaces allow the learning spaces to expand outside the classroom. In our plan, this is floors 2.5 to 3.5, and it consists of grades 3 to 5, and then below the floors 1 to 2, that consist of grades K to 2, and our shared spaces such as the library, gym, and cafeteria. Here in this rendered axon, this axon is showing how the classrooms can be utilized for different approaches to pedagogy, like traditional learning, play-based, and integrated curriculum such as music rooms. And then in this rendered axon of the gym and the cafe, it shows the relationship between the two. And as I mentioned earlier, the cafeteria seconds as a auditorium space.
Examining our structure, our building is comprised of glulam columns and beams. Our reason for using carbon sequestering materials was 1, for the environment, secondly, for ease of transport due to them being manufactured in Vermont, and third, for weight and making it much easier to assemble. All of this is supported by a ferric-based foundation. Ferric is a material made from glass and steel byproduct and sequesters carbon when it hardens. Moving into our section details, our building utilizes straw bale insulation made from prefabricated panels in Vermont again. Our reason for choosing straw was because of its ease of access, its price, and how easily it can be delivered to the site from Vermont. In our roof detail, it highlights the thickness of those panels, which are roughly 18.5 inches thick, and how we also use it in our roof to further insulate the space. In this detail, we can easily highlight our ERV system, which runs in a secondary wall. We chose to put those systems within a secondary wall rather than through the straw for ease of maintenance for any janitorial staff that could be within the space. And then finally, in the footing detail, it highlights how the ferric connection works, supporting the straw above the floor to prevent any sort of decay that could occur, and then also further insulating the building from the ground. Additionally, you can see the geothermal radiant floor system, which uses rigid insulation to enhance its ability to heat the floor that it's on. Moving into a straw bale assembly, most of these straw bale frameworks come prefabricated from Vermont. However, those that attach to the foundation can be first bolted in, then the additional framing can be added, after which cross bracing is attached, and then there is a lime finish put over it for improved vapor performance. Finally, our comparison between a standard wall and our current wall. So on the left is a normal 6-inch framed wall with pink insulation or fiberglass insulation with an R value of 16. In contrast, our wall on the right totals to 24 inches, but 18.5 of those inches are exclusively straw bale. This gives us an R value of 33, making it a much better performance. Although the wall thickness is thicker, we effectively utilize the space in our site to make it effective.
And that concludes our presentation thus far. In the future, we'll be reanalyzing our system efficiency throughout the remainder of the design period and finding ways to make our systems visible in the design in order to incorporate them into a learning curriculum. And we thank you for your time, and we'll take any questions.
Thank you so much. I'll hand it off to Catherine and Patricia.
Go ahead, Patricia. You can start us out again.
Okay, so one of the first questions I had, and I'm familiar with where Roxbury is. I was looking for in the presentation, but what have you done to kind of understand the community, understand the demographics or the needs, their teaching styles and stuff like that, since it's such a specific site?
So beyond some of the statistics we mentioned in the introduction of the different types of families that live in the area, the demographics of those families, we also are adhering to the Boston public school system. So a lot of our curriculum is deemed by the public school system itself, but we are trying to kind of work well within the limits of that school system, but try to adapt that program to create different curriculum that, like we were saying, is more play-based and kind of loosens the stress of school kind of on the children.
To further add on to that, we had experience touring a school, Epiphany School, where we were able to interview teachers and other staff about how they go about their daily work, basically, and how students interact with their environments. And from that, we were able to conclude basically how circulation plays an integral role and how that school actually lacks it, and how they need, what else students would need. For example, we interviewed their art director, who suggested to us having these auxiliary spaces that can be used for students to further adapt their creative minds to develop something they were actually interested in.
Thank you. Another question, when it comes to learning flexibility styles, I think there's perhaps opportunities there. Also, building as a third teacher, I don't know if you understand that concept, but there's, I think this is just a feedback, someplace to take the design. The opportunities, especially in that section, if you could go back to that, the cut section, you can see the geothermal, you can see the stack, I think it was this one, right? So, as we design schools for students, there's many opportunities to show off the way the building is working, right? So to have the building teach students that it is that it's using geothermal, that it's the exterior windows are, venting the heat. So I think that's an opportunity to explore, like, how do you expose that and use that as a learning opportunity and allow the building to teach students about sustainability. And the last thing was the materials. I think I heard a lot about Vermont and stuff like that when you were talking about the building materials. And I think I could encourage you all to look outside of traditional materials and think about maybe more unique materials to the location or to the project or to the school district or those things. And last, if I could, sorry, Catherine, the site. I just have a question about how you've positioned the building on the site, since you have that site plan, if you want to go back to that. How, I'm kind of, doing the bird's eye view question, but there are some moments in the site where, like, the way it's sitting right now, you've created some pinching moments. So maybe talk about that, why that's happening, or maybe that's an opportunity to explore further.
So the site actually has a 36-foot drop in a grade. So we've had to play around that because we've been kind of really designing it section rather than plan. So this was the plan as a result of section. And that's why it kind of jogs at these points here. And we also kind of using that grade because we don't want to dig into it too much because of its functionality towards collecting water for the building and our gray water collection system.
So I'm going to watch our time, and I know Sam's going to help me with that as well. I really thought the pieces that you presented were very strong, and I loved the detail. So I commend you on that. What I did think I missed, or we should go over maybe a little bit more, was your overall EUI, your market analysis, I'm curious about your adherence, since this is in Boston, and I am familiar with Boston Public Schools and their indoor environmental quality, their monitoring of indoor environmental quality. I kind of thought a few of those technical elements on the engineered systems side instead of on the architecture. And I know you've got the structural, you've got your wall sections, all of that. I maybe speak to a little bit more of the engineered systems from an HVAC standpoint and kind of the ROI market analysis aspects.
So our EOIs are, we actually did have 3 separate EOIs for each of our spaces because they're all very different in terms of volume. So for our main atrium space, we have a EOI of 30. And then for the classroom, each classroom is 22. And then the cafeteria is 18. And then our operational carbon is 137,438 kilograms of CO2. And then solar collection is 276,000 megawatts an hour. And the annual water collection based off of our total roof area is 166,684 gallons. I'm reading this all off of our project information sheet currently. Just wasn't part of the presentation.
Okay, thank you. And we are at time, unfortunately. So thank you, everyone. Thank you for an excellent presentation from Wentworth Institute of Technology. And we will move on to our next presenter, Concordia University. We'll give you a couple minutes to come on screen, pull your slides up, and be able to bring your slides up.
Let us know if you need any assistance.
Yeah, feel free to come off mute and let us know what's going on too.
Are you able to see our slides?
Yes, we can see your slides now. Catherine and Patricia, when you're ready, will you give me a thumbs up? Great.
I believe we're just waiting for one of our colleagues. She was in the meeting and just got kicked out after trying to share the slides.
I think I'm back.
Okay.
Oh, she's back. Never mind.
All right.
Okay,
All right,
great.
so can we begin?
Yes, let's go ahead. And
All right.
Concordia University, let's start now. Thank you.
Perfect. So today we'll be presenting the retrofit of our educational building, which is located in Quebec. So on the next slide, we'll be able to see a few pointers we'll be going over today. Our team is composed of an HVAC division as well as an envelope division. The structure of our building will, however, remain intact. So a little bit about the site that our building is located on. As Lori mentioned, this is an existing building. It is a school building that grade 7 or secondary 1, as they're called in Quebec, students live in and work in. It features classrooms, and there's a building next to it on the south side, as you can see in this image on the bottom left side of your screen, that blocks the south wall completely. So we realized early on that that was not going to be an option for solar panels, PV panels, because that wall is blocked. It is around 45,000 square feet, this building. It includes about 9 classrooms and a big cafeteria in the basement. As mentioned a little bit, insulation. So the building is surrounded by trees and has low direct sunlight. This was a problem when we were talking about PV panels, but there is a high incident radiation on the horizontal plane. So the roof of the building is an option.
So for our design goals, it's to extend the life of the school of the building by 30 years. It is also to reduce the energy efficiency by 50%, as well as have 15% of this energy as renewable energy. As we can see, this will be done through the complete renovation of the building envelope. We're also redesigning the HVAC system to have FCU and DOAS. We're also going to add PV panels on the roof, and the windows will become triple glaze in order to maximize, to minimize the heat transfer.
So to jump into the energy performance of the building, we ran both a baseline energy model as well as a model of our new design on eQuest. And upon our preliminary design, we've already decreased our EUI to just around 30. So we've already halved that. And this does not include any of the PV panels that are going to supply an additional 130,000 kilowatt hours yearly. The biggest concern for us when we were doing the design is the fact that this school is going to be occupied year round. So it's not only heating consideration, it's also space cooling. So we had to pay careful attention to that design.
Sorry, I was muted. For the HVAC system, every floor was designed to have different zonings. We really went with, depending on the facade, if the room is interior or touching an exterior wall. And that's how we designed our zoning in order to design then our HVAC system. So on the left, we have the ground floor. On the right, we have the second floor. And as an example, here on the left is the basement with, it only has one zone in this situation. So on the right, we can see our preliminary HVAC layout for design for the supply and return.
So here we have the retrofit HVAC system that we have decided to implement in our building. We will be doing a DOAS, dedicated outdoor air system, with fan coil units to each zone. As you can see here, there is also a sorry, forgetting the word, a heat recovery wheel on the DOAS system. So in the winter, the cold air coming in will be heated by the outdoor air being released back into the environment. So we're going to recover some of the energy that would otherwise be lost to the environment. There will also be a boiler in the basement. It will likely be gas powered because the existing boiler is gas powered, but we're looking into electrical boilers as well.
So we had initially selected an EIFS wall assembly. However, when we noticed that the R values were too low and that increasing the materials would pose a risk to fire standards, we opted for the following wall assemblies. So the main wall, which will encompass classrooms, hallways, and offices, can be seen to the right. We chose this assembly due to its simple constructability, its ease of replacing and maintaining materials, as well as its affordability. To the left, we have the auditorium wall, which encompasses a very large space. This building assembly was chosen due to its high performance, its long-term durability, as well as its fire safety. On the next slide, we could see the R values for our auditorium wall, our school wall, our below grade walls, as well as our roof and windows. These are demonstrated with the green lines, and in blue, we can see the National Energy Code for buildings. And as we could see, our R values surpass the requirements set by energy standards.
So in terms of designing the building envelope, special attention had to be brought to assess and mitigate any thermal bridging in the assemblies due to the fact that it was a steel stud design. So on the main wall, we're in fact using polymer brackets to maintain an effective R value of almost 12.3. That's an SI, so about R70. While on the main building, we're in fact using foam thermal breaks right behind the fasteners to achieve an R value of R50. In terms of the windows, we carried out an optimization of the building with regards to the window to wall ratio, and we came to a 30% gross window to wall ratio. We've selected to use triple glaze windows, both for their thermal performance, as well as low solar heat gain coefficient, and additionally due to the additional soundproofing ability that this has compared to double glazed windows. They will both be fixed and operable models on the building.
Following is the cost estimation. This is a preliminary cost estimation. It is not complete, but it does come out to 1.8 million with the retrofit of the walls, the roof, as well as the windows and the HVAC system.
Some of the next steps, we need to design the HVAC for the auditorium, which is on the north half of the building. We need to size the boiler for the classroom portion, as I mentioned earlier. We need to design our lighting. We need to design our PV panels. And we are going to look into adding a building automation system to ensure that the building is controlled well.
That's it. So thank you for listening.
Excellent. Thank you so much for your presentation. Catherine, I think you're up to start this time.
Could you go back to the slide with the picture of the exterior? Because I see your new wall sections. I understand. No, keep going. Where it's actually a physical picture of the building, which it looked like it was a complete brick exterior. So talk me through how you're actually going to retrofit that.
So essentially, we're aiming for a deep energy retrofit, and we've opted to fully redesign the building assembly. Although it's more costly, we actually wanted to get rid of the brick entirely. The brick is a recyclable material, of course, so that can be used towards, we're not just throwing it out. But we've opted to go with an assembly on the exterior. In fact, that will be a bit more durable and resilient. So on the main building, we are dealing with metal cladding, and on the auditorium, we actually want to install HPL panels, some laminated panels for more aesthetic purposes. And the benefit of those is it's very low maintenance. Installation is easy as well as replacement.
And then last question before I throw it to Patricia. Since you have the cafeteria in the basement, that offers an opportunity for some heat recovery there. What have you considered with the basement and especially like your cafeteria equipment? And one more thing, I thought you said at the very, very beginning that it was a residential school. And so I didn't see anything related to that in here. So I'm assuming that students have a separate building for housing. Maybe clear up those two things for me real quick.
It's not a residential school, so it's very just like a school for secondary one students, and next to it is a sports complex that is connected, but we're only looking specifically at the school because the sports complex is much newer.
Great, I'm sorry for my confusion. Okay, cafeteria in the basement, just super quick, so Patricia has time. So you've got heat load down in that basement. What are your thoughts on how you're going to be able to recover that or use that effectively?
So we're really gonna look with the heat recovery wheel. So the return air is gonna go back up to the DOAS systems, mixing in with also the return air from the rest of the building. So this is gonna allow us to have the air coming into the building through the DOAS to be heated almost to capacity, well, to the load that's necessary in the building.
We should also clarify that the kitchen does not have any cooking materials in it. There's no stoves or anything. It's just for eating. Yeah.
That is the clarification.
Sorry, missed that one. Yeah.
Quickly, I'll just ask about, since this is an existing building, what are the investigations that you've done for accessibility?
In terms of accessibility, we're looking to improve that. In fact, based on the sort of exterior accessibility of the building currently, you essentially have stairways up to the first floor, or in fact, what's the second floor, and other stairways down below. In our final design, we'd actually like to level that out entirely, so it can be wheelchair accessible and reduce that need for a large amount of stairs, even though you have a wheelchair ramp going up to the second.
Mm-hmm. Your initial site analysis sounded like, or at least in the beginning of presentation, you talked a lot about solar panels. Was that the focus of your site analysis? Did you do any additional site analysis?
Most of the analysis was with regard to the PV panels, although we still have a lot of improvement to do with the optimization of design, as well as just the shading. We're still looking into shading devices that are most likely going to be used on the second floor windows. Given that, even in summer times, you still get a lot of sun both on the east and the west, as this building is really southward facing.
Do I still have time?
7 seconds.
Okay.
So I think we'll call it.
Mm-hmm.
Thank you, everyone. I appreciate this excellent presentation, and yeah, good luck to the team. We will take a couple minutes here to let our next presenter, University of Cincinnati, come online and pull up their slides. And thank you again to Concordia University. University of Cincinnati, please proceed.
Can you hear me?
We can hear you now.
All right, sorry about that.
Okay.
All right, I can start again. All right.
Yeah, let's go ahead and start over then.
All right, sorry about that. All right, hello everyone, or hallo allemaal if you're from Houten, Netherlands, where we've created the Houten School for Duurzaamheid, which translates to the Houten School for Sustainability. Our team is composed of 7 multidisciplinary designers and engineers, featuring Raya, Jonna, Casey, Mateo, Joe, myself, Simon, and Maddie. So when approached with the task of designing a net zero school focused on sustainable learning, we had 4 key steps outlined in the process from start to finish. First, we had to develop a powerful experience by studying the surrounding environment of Houten, create and establish a design philosophy based on the cultural knowledge of Houten. Then we utilized the building's energy savings and used them as an inspiring educational tool for students. And finally, we were able to maximize and disperse surplus energy back to our neighboring community. So with those goals in mind, welcome to Houten, a city known for its heavy use of bike transportation, preserved historic structures, and fantastic cheeses. Located in Northern Europe, Houten's climate closely relates to that of Portland or Seattle, so you can expect high humidity and mild temperatures. So we closely looked at sun and wind paths to establish the key energy saving components of our design. Our established site is the northernmost area on a net zero corridor, which as you go south features an office, RV sales and mixed housing, and senior housing with similar goals in mind. Houten's town center is located across the canal to the west, and the site neighbors a residential community. So now with our environmental references ready, we're able to begin the development process. And in early development, we took established roads and pathways into consideration when choosing entry points, as well as areas for bike parking and gathering, with the goal of encouraging explorative interaction with the building. We also took inspiration from neighboring facades and developed our building's material in a complementary way. We were then able to develop the ground floor as a public gathering space, while the private upper floor is composed of a west, central, and east wing system, each featuring their own ways of generating passive energy. And as seen here are some roads, bike paths, and pedestrian walkways that we've outlined that are established at the site. So whether you come to school via bike, bus, or car drop-off, or from one of the other net zero corridor buildings, there is always a clear and inviting way to enter the building and safely avoid car traffic.
And then this is our second phase. In the create phase, this allowed us to make design decisions around an educational experience based on net zero energy systems that are displayed throughout our entire building. And this is a shot on the west side of our building. And we utilize a wind wall, which is basically a kinetic sculpture that uses the same technology as a standard wind turbine. And each unit rotates, but is then scaled to the size of a typical brick that you would see deployed around Houten. And then this is showing how we utilize curves all around our project to signal entryways and promote a more organic circulation path. This organic nature is also evident in our east living wall to mitigate heat gains and losses, as well as absorb water runoff. Yep. And then in this key concept, we are highlighting our daylighting strategy through the center of the south wall that gives the first and the second floor very much daylight, and also doubles to help flush the building in nights with significant drops in temperatures. This view also shows the gable roof on the east side, which we utilize in our classroom spaces to allow for more daylighting and to reflect the typical roof form of the Dutch neighborhood that surrounds our site. And then the floor plans, on the first floor, we have more of our public functions with the winter garden and the central core. On the second floor, we have our typical school functions like classrooms, labs, but in the corners, we have our resource center and our makerspace, which is also open to the public. And then this is showing our circulation, where you can see that the more public spaces is around our central core of the winter garden, and our more private spaces on the second floor are more around the periphery. And then in our utilized phase, we showcase our smart energy systems to benefit the comfort and quality of all our occupants. And we highlight this on the west side, we have our wind wall. On the east side, we have our living wall. And then in the center, we have our solar carve, which utilizes for our winter garden.
Here you can see many of our passive design strategies, such as our solar panels on our roof, our PV embedded glass on our south-facing curtain wall. The curtain walls are also very operable. We also have a highly insulated envelope on our roof. And the roof is also a green roof, and we also have the wind turbines and wind wall that we have discussed on the west side. For occupant experience, we really knew we wanted to go with an open floor plan to allow more collaboration between the occupants. One of the ways we did this was by creating a space between the second floor atrium and the winter garden on the first floor. This also improved the reasoning behind our sawtooth roof, because now we can cascade light from the second floor to the first floor. When we do use the lighting, we made sure it was specialty, like tunable white lights to help with circadian rhythm of the occupants, well certified, or a minimum glare light.
Now we'll take a look at the mechanical system. So supply air is generated with a ground source heat pump. Go ahead. The heat pumps are supplied by a ground loop where pipes route in our structural drilled piles around the perimeter of our building. And this allows water in the pipes to exchange free heat and cooling from the ground. Fresh air is supplied to the building with a dedicated outdoor air unit and is distributed to each zone with VAVs that respond to CO2 sensors in order to not overventilate unoccupied spaces. And this system saves 37% of energy annually compared to an ASHRAE 90.1 base case.
For our structural engineering diagrams, we have our vertical members in red and horizontal members in blue. Our location and how to requires a robust foundation to support the structure on soft peat soil. Our solution implements drilled piles that are connected to pile caps and grade beams just beneath the soil. This allows the structure to sit on top of firm rock found deep under the surface. Our superstructure is composed of steel and column beam framing system with support from load-bearing walls and trusses. We intend our steel to be sourced responsibly with low environmental impact in mind. To increase thermal resistivity with the steel structure, we also include thermal coating on steel members and thermal breaks between connections.
In order to accomplish net zero, we first maximize our building's energy performance and then supplement it with renewable sources. The envelope R value are improved from the baseline case. The mechanical system is upgraded to rely on free heating and cooling from the earth. Large south-facing windows provide lots of daylight through the space, which lowers the lighting requirement. And then after maximizing the building, the first renewable we considered was PV to the roof and a covered bike path. PV embedded glass decreases glare and also captures the sun's energy for usable energy. And a wind wall on the west side utilizes the strong west winds, as well as 11 wind turbines that are placed along the path. Next. And these come together to create an efficient, sustainable, and responsible building that's easy to see and interact with. Our building with total baseline values is an EUI of 29. And after maximizing the building with a better mechanical system, envelope, and end uses, we were able to bring our EUI down to 12. And then through the addition of all of our renewable sources, the turbines, the wind wall, the PV glass, the PV on the walkway, and the roof, our building was able to have a final EUI of -5, which is 117% energy reduction.
And we are unfortunately at time. Thank you everyone for your presentation. A gorgeous building. I think I started with Catherine last time, so Patricia.
Okay, so we just kind of finished that last section of a lot of elements that we're working towards the building. What is like the overall goal of how those elements want to work together? Like the solar panel, the wind turbines, embedded glass. What is the overall goal? Or like, is there a hierarchy? Are you prioritizing one over the other? Are there not partnerships, but one that, you know, pieces that work well together, that so they have to exist together?
Yeah, I can go. So we definitely wanted to have a building that was able to achieve net zero. So our first goal we knew we'd be able to get that most efficiently through solar panels on the roof. They have the best kind of bang for their buck when it comes to energy. But another goal was to have systems that are very easy for students to see and interact with. And that's where the addition of the wind turbine, the wall on the west side, and the PV embedded glass, they don't have quite as much return on the energy side, but it's a very good way to display to students that there are like new and up and coming ways to harvest energy, and they could see and ask questions, maybe have classes that kind of go into some of those aspects that they're able to see on a daily basis.
What are the opportunities for on the site for permeable surfaces?
So the entirety of the roof is semi-permeable, meaning it's a green roof, so extensive. That'll help with surface runoff. The lower level roof here that you see in the bottom left image that's displayed on the screen is another living roof. So the entire surface of the building is permeable and is water collecting. And throughout you'll see beds, flower beds, which are all permeable membranes. There is a lot of pavement, and we were working with a very urban environment. So it was difficult in ways to kind of situate it with and have enough access to the site without overwhelming it with foliage and flower beds.
Okay. One more question if there's enough time for Catherine. The exterior material looks like it's all brick, and that's intentional.
Yeah, we went with that mainly because it's in a very historic area. It's been around for centuries, so we kind of wanted to pay respect to the area while also utilizing as many of these renewable systems to not overimpose ourselves on the site.
Okay. Thank you, Catherine. It's all yours.
Thank you. We might flip back and forth. Go to your initial baseline EUI. I think you said 39, maybe 30. 29. Yes. There we go. Okay, baseline of 29. Now go to your floor plan of what. So this is a high school. It's targeted towards students interested in sustainability. I see one lab, one makerspace, another lab room. How did you get to? I think there's a mismatch between my teacher hat just came on. Okay, teacher hat came on. Is there a mismatch between curriculum offered for this age or type of student and space types and baseline EUI? Maybe just rethink that. A high school for this with STEM education for I think 150 students. Maybe just check that. I've not ever seen a baseline 29, and it could just be me. I've not ever seen a baseline 29 for these type of spaces. So did you guys check that? And maybe you're like, yep, we checked it and here's my source. I think that would be my only comment.
Yeah, I think that's a great comment. And we used Cove tools for our energy analysis. And I think that you are correct that it would be beneficial to us to go into those lab rooms, that makerspace, and kind of think more through specifically what equipment could be in there, as well as the kitchen. And I think you're right that we are missing some internal loads. So that will definitely be something that we can dig into right as we move on with this project.
And then last question, do you have a price per square foot for construction? Get that too.
We do. It's in a report. I didn't know if anybody remembered it.
It's in the report. Okay.
Top of our head. I think it was 1,300 euros per square foot, I believe.
Yeah, and our cost analysis is kind of the next process going forward, but we want to offset as many costs as possible.
Okay, I see it now.
Thank you. We are out of time. Thank you very much.
Thank you.
Thank you.
Thank you.
Yeah, thank you to the team and a great presentation from University of Cincinnati. Next up, we have Oklahoma State University. We'll give you a couple minutes to pull your screens up and pull your slides up. We'll give the jurors a couple minutes here to switch over to your project as well.
Okay, I think we're ready if you guys are.
You ready to go, Catherine and Patricia?
Yeah.
Great.
Okay. Oklahoma State, feel free to start.
Hi, so we're here representing Team OK State. I am JC, the team lead. And then we also have Matt and Emily here with us. And so today we wanted to introduce you to a lost treasure of our history and our local community in Stillwater, Oklahoma, the Washington School. So the Washington School is a local gem hidden by rubble and poor additional infrastructure. It is located in one of the southernmost areas of Stillwater that was historically known as the Bottoms. It also began as a segregated school. Its location caused frequent floods, resulting in floods of segregation. People like Karen, pictured on the right, were displaced from their homes and scattered across our city. Karen is an alumnus of the Washington School and a local community member of Stillwater. We met with Karen to further understand the historical significance of the building in relation to her community. She mentioned that there were many stories of adversity that she faced, along with the Black community in Stillwater. And she also mentioned that the most memorable part of the school was the auditorium because of the events and the community gathering that it created. So we saw this as an opportunity. It rests across the street from a local splash park. Now I want you to think about this. How many people play and pass this school day in and day out without even knowing how much history this treasure holds? So with this, we made a few goals for our Washington School. We wanted to maintain and highlight its history through adaptive reuse strategies. We also wanted to help rebuild the lost community by designing an educational arts program, restoring its original intents, while adding value to the community through an additional memorial park on the west side of the original building. We maintained the original 1900s T-shaped building and revamped the footprint of the additional wings and centralized the classrooms. Through the multi-purpose gym, the Washington School can host events outside of the school hours, and the added cafe can help generate funds for the school as well. The Memorial Park allows the community to gather and learn about the history of the school through the reuse of the deconstructed brick of the school. Sculptural pieces are created with this brick and placed throughout the park. And also to address the flooding, permeable paving is added to the west side of the site to mitigate the runoff before it hits the lower southeast side of the site where the water retention and bioswales are located. By maintaining the existing structure and utilizing lightweight steel framing, we are able to lower the cost of the construction for our Washington School. For the school addition, we utilized a subtle tan lightweight stone veneer to highlight the existing school's brick. Through this selection, we also added rigid insulation to the new and existing structure to bring our wall assemblies to our values of 23.69 and 15.22. We also selected 46% visible light transmittance to help with our cooling loads. Our LSG ratio is also 2.3 that allows for more light to be transmitted without added heat gain. In selecting our wall materials, we tested options through Tally lifecycle analysis software to reduce our global warming impact of the exterior walls. Our first option, we tested a full new construction as if we took the whole existing masonry building and demolished it and completely replaced it with load-bearing stone masonry. In option 2, we tested an adaptive reuse strategy with the use of the existing brick walls and additional stone masonry walls. With the use of adaptive reuse, the brick walls decreased the global warming impact by 51%. So then we ran a third option and found that we could further decrease that impact by an additional 2.6% if we swapped the stone masonry walls for stone veneer panels. So we opted for the third option and selected the adaptive reuse of the T-shaped building walls with the local Texas limestone panels for additional exterior walls. We not only looked at the materials, we also tested the daylighting of our building to maximize the daylighting of our site. We were able to obtain a higher foot candle level than the required code in each classroom space through our skylight design. In conjunction with running our tests and selecting materials, we also continuously tested our Washington School through Cove Tool. Our baseline model with code minimum efficiencies and 30% glazing is already lower than the noted target EUI. And through our material selection, added insulation and shading devices, and our more efficient glazing and daylighting testing, we were able to lower our light loads and bring our EUI down further to 15.08. To further reduce our loads and reach net zero, we added PV panels to the south and east rooftops of the school. There are two systems, one panel system sitting at 27 degrees, producing 21 kBTU per square foot, and one at 60 degrees, producing 23 kBTU per square foot. We also selected to utilize ground source heat pumps, lowering our EUI to negative 0.54. Through these environmental decisions, we integrated the systems into the school to maintain its historical context. We implemented underfloor ventilation in the gym space to allow the large truss to remain the centerpiece of the gym. Air handling units were also sized for 3 different thermal zones to help further lower the cooling load in the summer. And lead materials were also selected through the interior design of the building. Sound absorption panels are added throughout the classroom spaces to help lower the sound transmittance. And the gym truss remains the centerpiece of the original building, and movable furniture allows for a variety of community spaces. And the courtyard space also allows daylight to filter in through the school, and it utilizes itself as a further opportunity to teach students about information outside of their classrooms. Throughout the other spaces, such as the cafeteria and small additional library, biophilic design is utilized to evoke creativity through the senses. The exhibit space also allows for partitions to be put in place to display student work or information about the history of the school. Not only does the cafe help bring revenue to the school, it also helps reconnect the school to the community. With this being said, we welcome you to our Washington School. Through the initial design of the Washington School, we hope to bring more awareness to a lost history of our community. We have learned a lot about not only net zero design through this endeavor, but also as an important piece of our history within our community. We hope that you are just as excited to see what the school can become as it currently stands as a candidate to become a noted historical building. We hope to further improve our design systems and integration for the next phase of this project. Finally, we wanted to thank you for your time, and we open to questions.
Excellent. Thank you so much. Catherine, do you want to kick us off this time?
Sure. Just a quick question on your project data on your sheet. I'm confused by your construction cost. Wondering if that's a little bit of a typo. Is it 17.8 million?
Yeah.
Numbers out there. Okay, gotcha. It's okay. The other question I had is can you on the slides go back to your floor plan of the existing building? Yeah, perfect. Current teaching and learning pedagogy involves the addition of more maker spaces and also collaborative learning. So I know that this is an existing building, and I know that we want to respect kind of that historic nature and all of that context, but was there any consideration done for how these classrooms, how the space, the interior spaces needed to be modified in order to meet current pedagogy?
Yeah, so we actually, right before the semifinal completion, we mentioned adding to further develop it in the next phase, adding some collaboration spaces out through in the hallway. We have a really wide hallway. And so originally that's kind of what we were thinking, but we didn't get to further develop it. So for the next phase, we were hoping to integrate some of that, and then also like integrate some of that space in between the walls of the classrooms. And then the art room and the band room, we saw this as more of like a charter school, like a learning like art school for students around like elementary, like middle school age. And so we also want to utilize the courtyard space as like an outdoor learning space that could be utilized for play, but also for like learning space that we'll develop further in the next phase.
Great. Go ahead, Patricia.
Okay, thank you, Catherine. So for programming, I see in the beginning, you did a lot of work on the history and you found someone from the community to work with. So is this program something that was generated together through that process?
Yeah, so we actually worked with some collaborators in the history department at our school. And so they have been working on helping getting this building to become marked as a historical landmark. And one of our professors, one of our faculty, Professor Sarah Ra, and also Dr. Manzi, they are part of the Stillwater community, and this was brought to them. And they saw this as an opportunity to just help bring awareness to the site and just bring more awareness of the history to our community.
Okay. In your programming discussions, were there ideas or talks about further growth or, future growth?
Yeah, so with the memorial space, we were also proposing like a park next to it. There's the splash park across the street. So we thought this is a great way to integrate the community into the site and bring people in. And then also the cafe helps generate some revenue for the school. And the gym can also be utilized with the movable furniture for any kind of community events or school events as well.
I think I was trying to ask about the size of the school, and the way that your footprint is currently. How will you mitigate possible growth of students in the future?
Oh, yes. So to help with that, what we did is we kind of followed the original footprint of the building, which was actually smaller. We ended up bumping it out a little bit further to help with that. But also there are other existing schools near here. So we were hoping for this to be more of like, if you wanted to have your kid go into like more of like an arts program or like with band, they could go here. But we also do have some like other elementary schools and middle schools located near our site, further north of our site.
Okay. Last question, what about outdoor learning spaces?
So the courtyard space, we wanted to further develop it to not just include play space, but for the next round, think about all of our roof drainage kind of slopes into the space and how we can incorporate some water retention learning objects in that space. And also just like showing them how like different like rain chain systems work and things like that.
Could you just switch to the floor plan one more time instead of this site view?
Yeah.
Something to consider, just because this is an educational building, is nurses' suites. And so that has an impact. If you look at the epidemic task force, the work that ASHRAE had done recently about how we handle that, you might just check into how that is integrated, especially since you're having an addition. It wouldn't work well in the existing building, but you might look into that as well. Nothing to do with the energy, but just thinking about a well-rounded, healthy school and knowing that our occupant comfort and experience is also important in this competition.
We had one in the admin.
We are at time.
Thank you so much.
Yes, thank you so much. Thank you for the great presentation. And we'll give our next team a couple minutes to come online, which is the University of British Columbia and British Columbia Institute of Technology.
Hi guys, can you hear me? Hello?
Yes, we can.
Awesome. I'll try to share my screen. Okay. Awesome. You guys able to view my presentation?
Yes, we can.
Okay.
And we'll give our jurors just a couple more minutes or another minute or so to finish switching over to your project. So.
Absolutely.
Okay, it looks like we're ready to go. So, University of British Columbia and British Columbia Institute of Technology, feel free to take it away.
Awesome. All right, I'll get it started. Hello and welcome everyone to our presentation. This is our agenda for today, and I will be taking you through that journey with me. My name is Jian, and I'm joined today by my team members, Jeong, Leo, Gabriella, and our design partner from Vancouver Waldorf School, Miss Mary Henley. Following our design and industry partners for the project, and we are thankful to them for their support and guidance so far. Our design partner, Vancouver Waldorf School, were facing several issues like water leakage and infiltration through building envelope and limited outdoor and internal space usage constraints in their existing facility. Hence, they gave us a challenge to develop a design concept for the new purpose-built school on the same site, which provides comfortable, healthy, and inspiring spaces for its users and values responsible stewardship of our environment. Following are the spaces that will be making up the new school facility and act as a beacon for bringing the community together to celebrate value-driven learning. To achieve such a challenging task, we took inspiration from the students who had displayed their vision for a sustainable future on our first visit to the school. And that translated into the goals for our high-performance school, which comprises of a facility which has low embodied and operational carbon, along with healthy spaces to inspire and develop future climate crusaders. As our first step, we looked at the site from a neighborhood level to identify potential climate risks and opportunities for development. To a wider extent, besides being compliant with Energy Step Code, most of the measures for mitigation and adaptation are not mandatory, but recommended for resilience. At site level, following measures had to be taken based on initial assessment. 50-year-old legacy structure had to be demolished, new classroom pavilion and early childhood centers to be protected and reused, and increase in open space for outdoor activities. We decided to take a research-based approach to identify best strategies for our projects based on future weather conditions, precedent study in similar climate zone, and benchmarking for energy performance. North Vancouver is located in one of the mildest cold climates in BC, having less than 3,000 heating degree days. But this scenario is soon changing due to climate change impact, and hence future weather file was used to do the climate analysis. The psychometric chart shows that in order to feel comfortable in future conditions, planning for passive solar heat gain with sun shading, retaining internal heat gain, and adding dehumidified heat to a space are crucial strategies. Orientation of built mass along east-west axis is ideal for bringing in daylight and passive heat in a dark and gloomy weather of North Van as per the solar study results. But providing external weather shade during the month of June to September helps lower the heat gain and provides increased comfort. Moreover, wind potential can be captured during the months of July to September, as the temperature, wind speed, and relative humidity of those winds are apt to bring comfort. Conducting best practice study across Canada, US, Germany, and UK in similar climatic conditions provided insights of passive strategies like high performance insulated airtight envelope and glazing, terrace building section to bring daylight, solar shading to block summer sun, and use of green roof to reduce energy consumption. The active strategies included air or ground source heat pump for heating and cooling, demand control ventilation with HRV, and BMS to effectively control and optimize building energy use. We conducted a benchmark study as per NRCan, and that gave us two important things. Electrification of all building systems were needed to reduce carbon emission and reduce space heating load by going passive first, and thereby reducing the need for active systems. Moreover, a site EUI of 50 to 60 kilowatt hour per meter square was set after conducting regional and national level benchmarking study. Our solution for the proposed design started with a passive first approach to reduce energy consumption before using energy efficiently to create comfortable indoor environment for the occupants, and then generate clean energy on site to achieve a net zero project goal. To begin with, several resiliency measures were undertaken to strengthen the structure, create shelter space for the community, improve indoor air quality, and provide uninterrupted power supply for up to 3 days with the help of battery storage. We started with a simple cuboid form, which adopts the side slope and reduces heat transfer by earth sheltering. Then we broke the mask by adding atrium to bring in daylight in indoor space and exposed the classrooms on south for capturing solar heat gain. This enabled us to create green terraces, which can be used as extension space of classroom, thereby connecting the students to outdoor. Operable windows on north and south facade and central atrium enable stack ventilation and brings in fresh air. Solar and wind potential can be captured on site to generate clean energy further. Our design decisions were guided by site characteristics, climatic conditions, precedent study understanding, and programmatic needs of the school. As passive first strategy, we reduce the exposed envelope surface area on north by using site slope and earth sheltering to minimize overall form heat loss factor. Daylight and views were enhanced in the interiors by incorporating stepped terraces on south facade with seasonally controlled shading devices and by providing indirect light into atrium through daylight monitor window. Moreover, gymnasium receives daylight through clerestory windows on the roof landscape. As third passive strategy, low embodied energy natural materials with high thermal performance were selected for building envelope to reduce carbon emission and improve well-being through biophilic design elements. In addition, several initiatives were taken at site level, like green roof, rain garden, bioswale, and permeable pavers to reduce rainwater runoff, heat island impact, and enhance biodiversity. As a part of active design strategy, heating and cooling will be provided by air source or ground source heat pump. Ventilation can be provided with a combination of solar air heater and DOAS with HRV. Monitoring and control can be provided with the help of BS. Energy efficient equipments will be provided with the help of Energy Star appliances and LED lights, and clean energy will be generated on site with the help of solar PV and hybrid wind turbine. Decoupled HVAC system will be incorporated for school building, where air to water heat pump will provide heating and cooling through radiant ceiling panel, and demand control displacement type ventilation will be provided through DOAS with HRV. We explored the benefit of each active system to provide assistance with decision making and explore the market for available technologies. Along with passive and active system, several demonstration technology will be used throughout the building to educate and engage users. We did some early stage parametric analysis on our passive and active strategies in Autodesk Insight, and we were able to achieve the site EUI target of 65.9 kilowatt per hour per square meter, thereby also meeting the source EUI target of 190 kilowatt per square meter per year. To conclude, we'll be engaging in the following listed tasks for final design submission to complete the requirements of each contest. Last but not the least, I want to thank you for listening to me patiently and request you to embark on the solar decathlon with me. Thank you.
Excellent presentation. Thank you so much. Let's turn it over to our jurors now. Catherine or Patricia?
So,
Oh, go ahead.
I'm sorry.
Go ahead.
So could you go back to the mechanical systems? I heard you mention displacement ventilation.
Yes.
Was that in the gym only?
No, it's in both the spaces, in classroom as well as gym auditorium space.
Okay. Go ahead, Patricia, while I regroup.
Sure. Just a clarifying question. Would you call this the school that was there previously a community school? Like highly engaged with the community? I saw pictures with lots of kids and people, so I thought.
Oh, the first slide? Okay.
Yeah, it was like the kind of the
Yeah, it's an
collection of
existing school, yes.
yeah, and it's
This one? Or not
yeah.
the first one? Sorry. Yes.
Right, yeah. It seems like it's an indoor outdoor. It was an indoor outdoor kind of
It
school.
was indoor outdoor. It was like a courtyard type building, ground floor structure. And that
Okay.
was the existing school, which
Sure.
was never planned as a school.
Okay, so
Interestingly.
then how does this new design kind of maintain that kind of personality that it had before? What are you doing to design for it to be like a community school, like as a label, but like to maintain that integration or the openness and the fluidness?
Sure. So we did apply the same courtyard level space in the atrium, but that's a covered space. But we created opportunities for them to go outside the classroom like they already had by opening up the terraces. as well as there's a community level space by creating a slope for the gym structure so that anyone and everyone who wants to just sit by and who are passing by, they can engage with that. And that particular block will be also used as a shelter in cases of any natural calamities or something.
Mm-hmm. With the demolition of the existing kind of structures on the site, did you investigate any opportunities for reuse or reclamation or relocation?
Absolutely. Not relocation per se, but I would say that I think there are a lot of opportunities to use existing roof rafters. And we couldn't look through the walls, but I think we'll make that effort to at least use 50% of the materials from those. And there's someone called Unbuilders in our region who do that work pretty well. So I think we'd be engaging with them.
And they're called unbuilders?
Yes.
Okay, that's kind of cool.
Yeah.
Catherine?
I think the only thing I would add, could you go over to the other site plan too? Thanks, Patricia, for asking that question about the divestment of the other buildings.
Oh, the site plan? Yeah.
Yeah, the site plan, where it said what was staying and what was going.
Yes. Just give me a sec.
And you've made sure to recapture all those programmatic functions that
Yes.
that were contained in those other buildings.
Yes.
And I'm curious that it's you're repurposing the 1993 building. Okay, gotcha.
Yeah. No, the 1993 is only these 3 classrooms, which we'll be retaining.
Oh, gotcha. Okay.
But we'll be removing this structure, which was never meant to be a school, but they habitated that like a few years ago.
Okay.
And that's
Quick
needs to
question
go on.
before we
Yes.
run out of time. How did this school itself perform in the recent last few years weather event where there was the over 100-degree temperatures for multiple days? You know,
They
I'm from
closed.
Houston, so I don't remember, but I know you had it.
Yes.
Did
Yes,
you look
absolutely.
at how it performed in that weather event?
They had to close down the school for a few days. That's the message that I got from them. Mainly because of no cooling per se, firstly, because of the heat wave. And they also said that we want to design for future heat wave, future, wildfire events, because they're very close to the mountain. And that's why they asked us to explore MERV filters and they can still run the school. So all of it was from a resiliency standpoint that they want to continue to run the school and also provide like a community shelter space, because I have faced that myself. I faced flood and earthquake, and I went to the nearest school because I thought that would be the safest for me.
So I like the fact that you had the best practices using the other schools in the area. And since you know that there was a heat event, it might be a good opportunity to capitalize on that in your storytelling.
Absolutely.
On how you're helping this facility with that type of resilience initiatives.
Absolutely.
And with that, we are at time. So thank you, everyone. Thanks for your presentations. And at this time, we are going to take a 25-minute break. And we will be back, let's see, it's approximately 11:40. So we will be back at 2:05 p.m. Eastern Time.
Thank you once again from my side.
Thank you. Thank you to all of our morning presentations. And we will see you in about 25 minutes.
Thank you.
Hello, everyone. We're just waiting on a couple more people to join, and we will get started for our afternoon session. Our next presenters are Ball State University. If the team is on and wants to start pulling up slides, we can at least get into that process. And Patricia, yes, there we are. So I think we have everybody back online. Ball States, welcome, and feel free to proceed.
All right. Good afternoon. We are IDA, Inclusive Design Advocates, a group dedicated to socially sustainable inclusive education, and we are proposing the redevelopment of the currently vacant Thomas Carr Howell High School. Originally built in 1940, with the last reported enrollment of 675 students, the existing facility includes over 300,000 square feet of space. TC Howe is located on the east side of downtown Indianapolis and serves 3 adjacent neighborhoods. When analyzing the greater Indianapolis area, our team identified a need for special education facilities within our target community, as 1 in 6 IPS students are reported to have a learning disability. In response to this need, our team has identified 6 design goals and has created TC Howe Development Center, a highly adaptable and inclusive environment for students with special needs. When discussing this redevelopment, our team took into account historical value, embodied in operational carbon, and occupant experience to come to the decision to demolish the northern portion of the existing school and create a new single-story classroom addition to the southeast. Furthermore, the demolition site is redeveloped into a park and includes public gardening, play, and entertainment spaces. The new TC Howe Development Center includes just under 80,000 square feet, reducing the overall square footage by 73%. During design, our team used logical spatial planning to reduce travel distances and create centralized common spaces in order to provide students an optimal learning environment, despite our reuse of a historic building. Additionally, the creation of 2 centralized courtyards encourages access to nature and allows for natural light within each classroom.
The site is located in climate zone 5A, which is heating dominated. Sunlight and solar radiation potential informed our design decisions. The new construction building envelope consists of an airtight CLT and polyiso, which is continuous and reduces thermal bridging and air leaks. The existing historic portion has been retrofitted with 2x6 studs and blown-in cellulose, which we found sequesters carbon through our analysis. Through our global warming potential analysis, we found it most beneficial to reclaim limestone, which will be reused in the new facade, and brick, which will be reused as slag. Our new material selection was driven by environmental impact. The CLT panels sequester carbon, and the polyiso insulation was selected out of a comparison of many different insulations because it has a high ratio of R value to embodied carbon. The total EUI is 30.89. Through our iterations, we achieved a total of 51% spatial daylight autonomy. And based on our total footprint and EUI, we have potential to be net zero through 2 PV systems. Our HVAC includes a geothermal system that takes advantage of consistent ground temperature year-round. The VRF heat pump with a combined COP of 7 efficiently heats and cools without losses seen in conventional air ducts and has the ability to control temperature in zones. In our aim to enhance indoor air quality, we have decoupled the ventilation by adding a parallel dedicated outdoor air system with ERV, which removes contaminants and will deliver fresh air by thermal displacement ventilation. Comfort and environmental quality is a high priority, and the hallway incorporates a stack ventilation strategy where the stack is twice the height of the space it is ventilating for greatest effectiveness, which fully satisfies the cooling need of the classroom. Natural convection was an integral concept for the design, implemented in inlet and outlet placement positions. We saw an innovative opportunity in the existing south-facing gym masonry wall and purposefully integrated a trom wall addition. In the winter, glazing is closed for heat retention, and in the summer, glazing is open for ventilation. The trom wall offsets 30% of the gym's total heating needs. And from left to right, this diagram illustrates the trom wall, a standalone south-facing roof-mounted system with battery, an east-facing PV integrated facade system to match peak demand and provide shading, the rainwater recycle collector, and clear stories, which provide delightful daylight factors of 5% and 75% of the space and effective stack ventilation.
When it comes to occupant experience, the flex spaces will encourage social activity while connecting the two courtyards. As we can see on this diagram, the west courtyard was designed as a sensory play area, while the east one would focus on rainwater collection. Material-wise, we are looking at sustainable products such as a recycled metal roof, and for the interiors, we have chosen low VOC and carbon negative finishes. At the same time, color and interior finishes will also be used to improve wayfinding and to help distinguish all the school grade levels. For classrooms, the learning experience will be enhanced by applying elements such as easily movable furniture, partition walls, and a seating alcove to alleviate anxiety, while also introducing rubber flooring, acoustic clouds, daylight, and natural ventilation in order to develop a safer and healthier environment. At the new main entrance, where all the vertical circulation is now centralized, we have designed a set of ramps to serve not only as an architectural feature, but also to celebrate movement. The gym was also designed to serve as a the gym was designed to have self-sufficient systems in order to serve as a community resilience hub during disruptive events. So far, we have engaged with local stakeholders, education, architectural firms, and inclusive design specialists. Moving forward, we are very excited to continue this journey of exploring no limits education with high performance standards. Thank you. And now I would like to open the floor for questions.
Excellent. Thank you very much for your presentation. Catherine, do you want to go first?
Sure. Talk to me about what cost, what you've looked at so far on renovation cost, your return on investment, those kind of items. Market analysis, those topics.
So is your question on how we arrived at our cost estimate?
Yes, let's go back to that.
Okay, so it's seen here on the slide in the lower right-hand corner. And I think our case study included a lot of ASHRAE K-12 net zero case studies that we looked at. And just taking into account climate zone systems, mechanical systems, and total costs. And it was very interesting to see the estimated costs and the actual cost.
So, okay, so at $307 a square foot, you're saying that's for the retrofit?
This would be the total cost. Yes, including the retrofit.
Okay.
So it would be the historic portion as well as the new construction.
Okay, thank you.
Thank you.
Tricia?
Okay. Yes, I do. So is there a slide or image that clearly denotes the existing spaces and the, okay, thank you. Great. Okay, and so you mentioned square footage reduction and it sounded like that was successful. Why is that successful? In terms of like your design goals and the specific project?
Yeah, I can answer that. So we ran a virtual analysis. We're using the existing portion and using, and then subtracting part of that existing portion and adding a addition. And we found that it's better for the carbon per square meter. If we were to remove that due to the operation cost and the amount of carbon that would produce for that large volume. And it also aligned better with our occupants' needs, not having to span 3 floors and being able to kind of ground that plane a little bit better.
Okay, so the reduction was not so much of like a sprawl, but kind of like even vertically, just kind of, it was more about compacting. Okay, and when you did that, did you consider the ability of the new construction or just the whole thing being able to receive population growth or being able to grow with the city that it's in?
Yeah. So yeah, we did. We're in our next few phases too. We're going to look at some different phasing opportunities to expand around our site and while keeping that accessible route. So that's what we're trying to move with forward.
Great. There is a great image that shows the 3D spaces, or I remember you highlighted an alcove. If you could go to that. So I'm asking about that because what are the ways you've designed for technology to be integrated into the learning spaces? Yeah, that one. On, technology for teaching and technology for communicating.
Yeah, so I think the main design goal that we were trying to get with our classroom setup is flexibility and having the ability to, bring in technology to have these classrooms take different shapes as required for the students' needs and the teachers' learning needs. So we're imagining some, movable smart boards in that sense of technology for learning, and especially if maybe with this whole new Zoom world, having the ability to have a virtual classroom for maybe some students who are unavailable to make it in that day due to sickness or anything, without missing a school day if possible. So.
Okay. Catherine, do you have other questions?
Talk me through just a little bit more how you're using the geothermal plus the VRF.
And unfortunately, we are actually out of time. I'm
sorry.
I muted myself instead of unmuting myself to let you know that. So that's my fault. Sorry, but we are out of time. So Ball State, thank you so much for your excellent presentation today. And our next presenters are going to be College of the Canyons and Universitate Spiro Harat. I assume I did not pronounce that correctly, so I hope the team can correct my pronunciation there. Do we have somebody from College of Canyons on?
Yes, hello.
Hi.
We're just going to get our slides set up real quick to share.
Okay, thank you. And
All
Catherine
right.
and Patricia, are you two ready? Okay. Grace, take it away then.
Alrighty. Hello, everyone. The College of the Canyon Solar Decathlon team have designed a culturally responsive educational facility for the training and influencing of displaced and/or underemployed residents of the surrounding communities located near the village of Crisan, Romania. We prioritize multiple sustainable designs ecological and agricultural improvement, and work opportunities. Our educational facility is 11,132 square feet and holding up to 602 occupants. Researching the surrounding site, we found that 1/5 of Romanians have agricultural related careers. Romania overall is one of Europe's largest producers of sunflowers, corn, wheat, and soybeans. The Danube Delta is the largest reed bed and wetland in Europe, while also being the only biosphere reserve delta. Being Europe's largest purification system, it has become one of the most well-protected and famous wildlife areas, holding approximately 5,500 species of flora and over 300 species of birds. Our site along the Danube Delta is near the Salina Marina Port, the Black Sea, and natural reserves and parks. It can be a refreshing yet sticky environment with annual average perspiration of 9.4 inches and humidity being 78%, with average temperatures of 38 to 79 degrees Fahrenheit. This region includes extensive examples of unaltered rivers and lakes, dunes, sandbars, coasts, lagoons, salt marshes, and forests that can be observed through tours and educational practices through our facility. To determine building orientation and sustainable design strategies, we research Croissant's wind patterns. The average wind speeds range from 5 to 13 miles per hour, but it is not uncommon for winds to reach over 20 miles per hour. While previous research suggests that the wind comes mostly from the north, this study shows that winds can travel from all directions. From such observations, we realized that the wind is a key factor to renewable energy within the area. With this solar analysis, we've found in Croissant the annual average of sunshine is 2,267 hours, with July being their most sunny month of 325 hours, and December averaging lowest with 72 hours. For this solar analysis, we used metallic renderings to pinpoint the location of the sun. As the sun rises from the east, we can see the effect it has on the site as it rotates counterclockwise. Sustainable designs were thoroughly considered based on the overall climate conditions and immediate surroundings. Our main source of renewable energy is wind energy, supplemented by hydroelectricity. We want to keep hydroelectricity to a minimum, however, to not disrupt aquatic life. However, other strategies include natural heating and lighting, water recollection, and permeable concrete. Our 5-acre site is surrounded by a variety of vegetation, bodies of water, and vast wildlife. Our educational facility is broken up into 4 pods. Starting from the left is the kitchen, the dining space, the greenhouse, the multipurpose room, and the exhibit. The south elevation shows what occupants would see when approaching the site from the dock. Because of generally colder weather in Croissant, we focused on heat gain, which determined the placement of the windows. Here we have a perspective view of the kitchen and dining space, as well as the greenhouse. This greenhouse is located in the courtyard and is surrounded by raised garden beds. The garden not only provides produce for the kitchen and dining space, but is intended to teach visitors different forms of gardening. Variety of plants can be grown from root crops like carrots to vines like cucumbers. However, because winter can limit growing opportunities, the greenhouse will host hydroponic towers, which allow growing all year long despite weather conditions. The kitchen and dining area can hold up to 194 guests that include loose tables and chairs to allow different layouts if desired. Pleated windows are located along the wall facing the courtyard. These windows create an even blanket of indirect lighting throughout the day so that guests do not experience glare from the sun or the reflection off the Danube Delta. This image shows the overall ambiance of the dining area with the sawtooth windows above and the pleated openings on the left wall. The most important element of the space that makes it interactive is the kitchen window that allows visitors to watch how their traditional dishes are being prepared using produce from the greenhouse. Next is where the main educational space is located, the multipurpose room. This space can hold up to 320 people. However, with a partition wall, this room can be split into 2 to allow different classes to be held simultaneously. The intention for all of these spaces is to experience traditional elements while learning about them through the architecture of the pods, such as the reed thatch roofing. Behind the multipurpose room are walls that are strategically sloped to allow the wind to flow through vertical wind turbines and ride the walls up and over the buildings to avoid any harsh direct winds. Moving on to the last pod is the exhibit hall that can accommodate up to 57 people. Behind the wall of the reception desk is the door that leads to the staff room and offices. This pod is the only one that has north-facing sawtooths because we wanted to have as much indirect passive lighting as possible to prevent any glare caused by the glass displays in the exhibit. The intent of this exhibit is to showcase the historical and current wildlife species and the overall culture of Quezon. The addition of glass display cases allow guests to move more freely within the space and be able to see them from any angle without any inhibiting views. This rendering of the exterior of the exhibit hall shows the sawtooth design and pleated windows. Aside from the pods themselves, there is a large walkway where visitors can roam. Birdwatching is a major tourist attraction in Quezon, so birdwatching shelters are included along the paths where visitors can observe while being protected from the weather. The walkway itself is set above ground to avoid disruption of the land and to allow roaming despite soil conditions. The landscape through the walkway will be restored by planting trees and other native plants to promote wildlife. Like the roofing of the educational center, here we can see fishermen huts with traditional thatched roofs. The simple organic approach allows for a more sustainable and permanent fishing spot compared to the traditional temporary shelters made of unsustainable scraps and harmful materials. Here we have a better view of the roof design. This front building is the kitchen and dining area. The roof design is strategically placed to collect heat during mornings and evenings, typically when temperatures are at their lowest. And finally, an overhead view of the roof showing a complete design of our educational center. Thank you.
Great, thank you so much for your presentation. Patricia, do you have any questions you'd like to lead off with?
Yes. So going to your sustainability, or you had a slide that says sustainable designs. Could we go back to that? I have a question about your proximity to water, and I am curious, okay, so you do have water recollection and hydroelectricity. Okay. Could you talk a little bit more about how those are specifically integrated into your design?
Yes, I can speak a little more about that, and I do apologize for the lack of video on. The weather's a bit severe here, so my connection's not the best. But water recollection, despite all the large amounts of flora and vegetation, wildlife, and so forth, it actually rains very little. I think the average there, she mentioned, is about 9.4 inches, which put into perspective, it's actually less than Southern California. On that note, we thought it was important to recollect any small amounts of rainwater. It does typically snow, so it would be the way the roof patterns are formed in that pleated section. The inward section of the pleats would allow that water recollection and specific deviation into these tanks that could serve as water irrigation for the plants and the nearby flora as well. In regards to hydroelectricity, we were considering doing low pressure power plants. I think similar to that would be a power plant Expo. I do, forgive me if I mispronounce it, but Expo Egliasu Finance, somewhere in Switzerland. But these small portions of power plants that serve sort of like a windmill or a small dam in a way. They could produce up to 37 megawatts or an average of 244 gigawatts of electricity per 10.5 meters of area.
Okay, and then how have you designed the walkways to work if there's a potential for the water levels to rise? Is that a potential? Is the water always the same?
We did consider that. The building itself has a minimum of has a mass foundation, but has a minimum of 3 foot rise. We do have multiple stairways and ADA ramps around the building as well. The pathways themselves are built with wood from the local area. And they are also raised a minimum of 3 feet with an addition of 1 foot foundation.
And last question for me quickly. The greenhouse is centrally located, but how does it work with the elevated walkways around and thinking about accessibility and just having like equal access or not having a long route? Could you explain that?
Yeah, absolutely. There is an ADA ramp on the left side of the access road. We would personally advise not to have access throughout the walkways. just simply because it's a wildlife area. So we would advise for them to be able to come back, safely into the premises. But if that was the case, we would also have multiple stairways and accessible ramps throughout we were aiming for at least 4 on each section, northern, western, eastern, etc. sides of the ramps of the pathway.
Two questions very quickly. With a temperature of 38 to 79 degrees Fahrenheit, what is your interior temperature range for the occupants? What is that interior range goal? You say natural heating.
We would have an HVAC system if necessary, which of course it probably would be. But the way we did the design of the roofing system itself, we ensured that we had enough openings or window openings for us to obtain natural heating from the sun itself. We actually did direct, in certain cases, southern openings, which is where we would attain most of the sun area. And as we mentioned, we left even more openings on the left sides so we can attain direct sun from the morning specifically and in the evenings itself.
Cost per square foot to construct.
That's in the first, second slide.
And I apologize if I missed it.
No worries, it's in the second slide. It's about 312. 325 to 350 square feet.
Okay, great.
We're just to elaborate a little more. We're using a lot of simple designs, as I mentioned. We're not using solar panels in this case, just for the lack of solar energy. But we are using thatching roofs, which has been used for quite a bit there. It's actually one of the classic architectural approaches. So we are saving a lot of costs by using simple methods.
Great, thank you for the Q&A there, and thank you for the presentation.
Thank you for your time.
Thank you. And next, we'll move to California State University, Fresno.
Can everyone see the slides?
Yes, we can, and we'll give the reviewers just another minute or two to complete and switch over to your presentation here. Okay. California State University, Fresno, team, I think we are all set, so let's get started.
Hello, this is a Sundogs presentation from the Laos College of Engineering, the Department of Mechanical Engineering at California State University, Fresno. Here is a picture of the Jordan Agricultural Research Center that we conducted this project on at the California State University, Fresno. Introduction. There are a plethora of options in the sense of energy systems, with renewable energy, specifically solar energy, being best fit for the high solar insolation that occurs in Fresno, California. Research centers like the Jordan Agricultural Research Center at CSU Fresno occupy lots of electricity, costing the university thousands of dollars. Equipping the JARC building with solar panels can minimize the cost of electricity with 3 potential solar systems: building applied photovoltaic, building integrated photovoltaic, or building integrated photovoltaic/thermal. The building integrated photovoltaic system would be best fit for the JARC building, and it is the only material that has a return on investment. As of now, the installation and integration of solar energy generation systems are not regulated at the federal level. Instead, there's several programs and policies that support the growth, such as the Modified Accelerated Cost Recovery System and the Federal Investment Tax Credit. These are at the state level, and specifically in California, the California Solar Initiative provides 2 incentive-based programs: the Single Family Affordable Solar Homes and the multifamily affordable solar homes, providing incentives for solar systems for families. While solar energy does have many benefits, solar panels have a life expectancy of 20 to 30 years, so the recycling of panels should be evident. However, less than 10% of the panels in the US are recycled due to the high cost of the recycling process.
The Jordan Architecture Research Center is the largest building in the area and has a high visibility. There are no large trees around it that would shade it in the near future, making it the ideal location. It will be utilizing the front and back sides of the building because they are exposed to the most sunlight. The front side of the building consists of 3 facades, which are 11 meters by 5.18 meters. And the back side of the building has a singular facade that is 9.8 meters by 10 meters. This gives us a total usable area of 268.94 meters squared, which allows for a maximum of 104 panels to be installed using the BIPV system.
I believe you're on mute.
I'm sorry. The first design that come up to our mind would be to install the solar panel with optimum angles. This will ensure that the solar panel would receive the most amount of sunlight. However, this initial investment cost is much higher than the money saved. Along with the cells, the rackings also need to be replaced every 25 years. Not to mention the efficiency of the solar cells can degrade 0.5% every year. So to use expensive racking system would not be financially wise for the long term. To fix this, another design is introduced, the vertical installation of the solar cells. So for this design, the solar panels are vertically installed on the new surfaces, and this will take up much less space. Not only that, the panels would have less dust accumulation, which would work well for a dusty area like Fresno. With all of this, the maintenance costs will be much lower, and it will result in faster payback period. The solar cells would also give the modern futuristic look to the buildings. The location that we choose to plant the solar cells will be strategically chosen to have the most amount of sunlight.
Upon running our simulations, we found that on a monthly basis, the levelized cost of energy was 8 cents per kilowatt hour. And this leads to a total levelized cost of energy for the entire installation to be about $1.97 per watt. And for profit wise, we found it to be about $12 to $20 or 12 to 20 cents per kilowatt hour.
Now, to make sure that the project is actually feasible, we went ahead and we calculated the payback period. We estimated the project to be to cost anywhere from 45,000 to 59,000. The annual revenue expected from this project is going to be 5,357. So taking account the annual revenue that the solar systems will be producing, and comparing that to the total cost of the project, we have an estimated payback period anywhere from 8.7 to 12 years. But taking into account the PG&E increase rates that have been in place here in California, we can say that by evading those costs, those increases from PG&E, we'll have a faster payback period, since in 2022 their increase was 11% alone. So basing off of those numbers and assuming that the trend will continue the same, we can assume that PG&E will be increasing their cost, whereas this will have a constant cost, so the payback period should be lower. Also, we will need to have to replace the entire system after 25 years, since that's the estimated life cycle of this project.
With the worldwide trend moving away from fossil fuels and towards form of renewable energy,
solar is definitely one of the most popular and one of the most feasible at a small scale. So for the students engaging in a start to finish implementation project on an existing building, it's a great opportunity to apply things we've learned as students. It emphasizes the importance of energy and importance of keeping up with demand. And we use things we've learned as students, such as economics, heat transfer, thermodynamics, manufacturing, circuits, and 3D modeling and simulation. In this project, several considerations for real-world application must be considered, such as conducting a feasibility analysis, determining the size and number of panels that will fit on the building, find the angle for the maximum solar production, and making it modular for ease of maintenance and replacement at the end of its life cycle.
And to wrap everything up, solar energy is increasingly being used to meet energy demands in buildings. The building integrated photovoltaic system involves installing solar cells onto the building structure. The study was conducted on the Jordan Agricultural Research Center at CSU Fresno to examine the cost implications of a BIPV system. The study found that a BIPV system costing a minimum of $44,000 to a maximum of $60,000 had a payback period of between 8.7 to 12 years. And opportunities for improving the BIPV system include optimizing the placement of solar cells, incorporating modular designs, as well as seamless integration into the building. Thank you.
Great, thank you so much for your presentation. Catherine, looks like you're already off mute, so I'll let you go.
Yep, I'm ready, thank you. Just two questions for me. Have you engaged with the occupants of the JARC to see if they're open to having solar panels on the building and what occupant benefits might be achieved by doing this project?
We have not spoke with the occupants of the JARC building, but that is a great recommendation and we'll definitely take that into account.
And then my last question, just real quick, my last question was, I didn't see, maybe I missed, what other analyses you would do in the next phase. I did see you said that you would do a feasibility study and actually determine the number of panels, but are there other steps that you would add as you move forward?
I can answer this question. Actually, we have one professor has a lab in the JARC building, and he is also the advisor of this team. And he actually, I mean, has a connection with the people working in that building. And our next step will be first, we're gonna have one or two senior design teams formed to work with our student team to design, to do the feasibility analysis. I mean, to do some measurement of the building, and also we're gonna work with the senior design team to see how will be the best way to install or possibly install the solar panel for that building, and also a second stage will be we have to explore whether it is allowed for us to how big the area we can use to install the solar panel for the building, because right now all our work is still on the paper. We do the calculation, estimate the cost, and next step we can actually we are physically working with the people working in the building to carry out the work.
And also, can I rectify? Yes, we have approached the Jordan building. They have given us their blueprints also to be take it to the next stage, and including the grid alternatives, a local non-profit partner. That is our next step also, another step available to us using grid alternatives.
Okay, that was Catherine's last question. So one of the first questions I thought about, and maybe you did include this in previous slides, but have you researched or confirmed the current usage or current energy rates of the JARC building right now?
Yes.
Yeah.
Okay, what happened, Fresno State has a very holistic bill. We don't have the breakdown per building. That is as part of our central plant upgrade. That one of the proposal is to have an individual building level consumption data. So, but what we are providing is a very little amount.
Unfortunately, we need the students to answer questions. So jurors, please disregard the questions from Ajit.
Give them extra time.
Okay, and we'll provide extra time for the students to answer additional questions.
Okay, do I ask a different question now?
You can ask the same question.
Okay.
I think.
Yeah, so did you look at the JARC building's current usage? And my follow-up question to that is, do you have a specific goal that you are going to reach with this design, and how will it affect it? Like sometimes people want to double it or triple it or something, or reduce it, or so do you have any goals in relation to where they're at right now?
I think our goal would be to apply this array to the roof of the JARC building to see how it turns out. That way we can implement this sort of design for all future projects for our university, because we are expanding and we want to incorporate as much green technology in future buildings and projects.
And then are you doing any analysis on, since the JARC building is your case study, are you doing any analysis on the feasibility? I guess that's going to come in the feasibility, but have you looked into that yet? Like structurally, what can it receive? How many panels, or what's the weight of the panels and stuff like that? Have you looked into what that might look like, or wind, right? The effects on those parts of the building?
We have begun preliminary studies. In the coming weeks, we will obtain more data to come up with a full design in the future.
Okay. Those are my questions.
Okay, thank you all. Thank you for an excellent presentation and for the Q&A session here. That wraps up our session for the day, and to our jurors, we'll see you bright and early in the morning. For the participants, I hope we'll see you on our announcements and session in the afternoon tomorrow. Thank you all. Enjoy the rest of your day.